The prevailing view among scientists is that current models explaining the universe's origin, most notably the Big Bang theory, remain the cornerstone of cosmological understanding. This foundational framework describes how stars and planetary systems emerge over time, eventually leading to the rise of life, including humanity. Despite its peculiar name, the Big Bang theory offers a compelling narrative of the universe's earliest moments. According to this model, all matter and energy were once compressed into an unimaginably small and dense point, far tinier than the head of a pin. From the singularity, a massive explosion unleashed the building blocks of the cosmos, initiating an ongoing expansion that continues to this day. However, as our knowledge of astrophysics and cosmology deepens, cracks have begun to appear in this long-standing model. The launch of the James Webb Space Telescope, JWST, the most advanced and powerful space-based observatory ever built, was expected to reinforce the Big Bang theory. Yet, in just its first year of operation, JWST delivered results that stunned the scientific community. Its unparalleled ability to peer into the farthest reaches of space has uncovered galaxies from such an early epoch that they challenge established timelines of cosmic evolution. These revelations have sparked intense debate over the possibility that matter might have existed before the event we currently define as the Big Bang. A turning point came when cosmologist Rohinatu, analyzing JWST data, discovered what is now considered the oldest and most distant galaxy ever observed, formed only a short time after the Big Bang. The implications of this discovery have rippled across the field, showcasing just how revolutionary the JWST's capabilities truly are. As the telescope continues to explore, it is shedding light on a formative era of the universe, one that may realign our understanding of how the first stars and galaxies took shape. The galaxy's JWST is uncovering possessed properties previously thought impossible so soon after the universe's birth. This unexpected surge in early cosmic structures has led to both excitement and skepticism, urging experts to re-examine and refine existing models. Beyond its groundbreaking discoveries, the JWST's design and position give it critical advantages. Orbiting 1.5 million kilometers from Earth, it avoids atmospheric interference and operates in near absolute zero temperatures, thanks to a massive tennis court-sized sunshield. Its gold-coated primary mirror and ultra-sensitive instruments allow it to observe parts of the universe that have long remained hidden. The telescope is currently unveiling the so-called cosmic dawn, a period occurring roughly 200 to 300 million years after the Big Bang, when the first stars and galaxies ignited. Yet, the processes behind this transformation remain fiercely debated. Theorists continue to explore the roles of dark energy, invisible dark matter, and the complex interplay of gas and dust in star formation. Now, armed with data from this unprecedented era, cosmologists are in a rare position to rigorously test their models. Whether these findings will reinforce or rewrite the rules of modern cosmology remains to be seen, but one thing is clear. The James Webb Space Telescope is reshaping humanity's view of the universe in real time. The James Webb Space Telescope, JWST, was expected to validate existing frameworks or perhaps uncover minor inconsistencies, but instead, it has ignited a wave of potential paradigm-shifting revelations. At the outset of its mission, expectations were modest. Scientists anticipated it might detect a few faint galaxies from the early universe. However, those conservative forecasts were swiftly outpaced. The telescope's first images revealed an astonishing array of galaxies of various ages, sizes, and luminosities, far more than anyone had imagined. This overwhelming influx of early galactic data has sparked a scientific race to redefine what constitutes the universe's earliest massive systems. As new findings continue to emerge, even the most experienced astronomers have been caught off guard. The scientific community and the general public have been captivated by the complexity and unexpected maturity of these ancient galaxies. While some researchers suggest that certain anomalies could stem from misinterpretations of the JWST's large-scale observational techniques, the prevailing view is that these discoveries mark a significant turning point in our understanding of cosmic history. These insights hint at a universe that is far more complex and enigmatic than our previous model suggested. The evidence gathered by JWST raises fundamental questions about the origins of the universe. Some scientists believe these anomalies can be explained within the framework of current cosmological theories, while others argue they may represent the first signs of a deeper, more layered cosmos. The central question persists: how did the structured universe we know emerge from the chaos of its primordial beginnings? The telescope's early results have the potential to dramatically reshape our understanding of the Big Bang and lead to new interpretations of distant galactic structures, possibly even changing how we see our own Milky Way. As Mark McFadden, a senior science leader at the European Space Agency, aptly put it, the goal of building instruments like JWST isn't just to confirm what we already think we know. It's a challenge and sometimes dismantle long-held beliefs. You never know what may be overturned. The vision for the JWST dates back to 1985, years before the Hubble Space Telescope launched. At the time, Garway, then director of the Space Telescope Science Institute, SDSCI, was tasked with imagining the next great leap beyond Hubble. Despite early skepticism, Garway and his team laid the groundwork for what would become the James Webb Space Telescope. Where Hubble excelled in capturing visible light, JWST was engineered to see in the infrared spectrum, a crucial feature, as light from distant galaxies is redshifted by the universe's expansion, rendering it invisible to optical telescopes. With its massive ultra-cold mirror, JWST can detect these faint signals and peer further back in time than ever before. The need for such a telescope became undeniable in 1995, when Hubble's deep field image revealed thousands of galaxies in what appeared to be an empty patch of sky. That discovery underscored how densely packed the early universe was and made the case for a more powerful successor. After decades of meticulous planning, development, and nearly $1 billion in funding, the JWST launched on December 25, 2021. By July 2022, it was fully operational and embarked on its groundbreaking scientific journey. Programs like the Early Release Science, ERS, initiative and the General Observing Program were designed to uncover the universe's earliest galaxies. Although initial predictions were cautious, JWST's first wave of data has already begun to challenge, and in some cases, overturn long-standing models of the universe's infancy. The latest findings underscore the critical importance of pushing the frontiers of exploration and investing in state-of-the-art technologies. With each new stream of data from the James Webb Space Telescope, JWST, scientists edge closer to potentially overturning long-held assumptions about the universe. When JWST's initial transmissions were released, the excitement was palpable. Researchers who had spent years refining their analytical models were finally able to test them against real data. Rather than waiting on the often slow-moving peer review process, many scientists opted to publish their early results on preprint platforms like AR-14. This approach allowed for rapid dissemination and immediate feedback, igniting vibrant scientific discussions, particularly across social media platforms such as Twitter, where experts engage with new theories in near real time. Cosmologist Rohin Naidu referred to this dynamic shift as science by press release, highlighting the unprecedented speed and public visibility of the unfolding dialogue. However, this rapid-fire method of knowledge sharing sparked debate. While it accelerated collaboration and insight exchange, it also raised concerns about the potential erosion of the rigorous standards traditionally upheld by the scientific process. Klaus Pontappadin, a lead project scientist for JWST at SDSCI, cautioned that the pace of discovery risked overwhelming the careful structure that underpins sound scientific validation. Still, despite the procedural challenges, the scientific community largely agrees that the benefits, namely, the sheer scale of knowledge being uncovered, far outweigh the drawbacks. At present, the Big Bang Theory remains a dominant framework for explaining the origin of the universe, detailing how stars, planets, and eventually life emerge from a singular beginning. Though the name may suggest an explosion, the theory actually describes a precise, science-based account of the universe's expansion from an extraordinarily dense, compact state, smaller than a grain of sand. From this point, energy and matter erupted outward, setting into motion the cosmic evolution that continues to this day. Yet as JWST peers deeper into the ancient universe, its discoveries are beginning to expose cracks in that foundational model. The detection of galaxies forming much earlier than current models predict suggests that our understanding of cosmic history may be incomplete. These revelations not only challenge key assumptions of the Big Bang Theory, but also hint at deeper, undiscovered principles that govern everything from subatomic particles to the vast architecture of galaxy clusters.